Good evening. One of the best telescopes in the world is the Anglo-Australian Telescope, or AAT, at Siding Spring in New South Wales. It's not the world's largest telescope by any means. It has a 3.9-metre mirror, and neither is it in an ideal site. For one thing, it's not on top of a mountain. There are no really high peaks in Australia. But it has a magnificent record, it's fully automatic, and is used for all branches of research. For example, with it, David Mayland has taken just about the best pictures of nebulae and galaxies ever obtained. But now, the AAT has just been equipped with an entirely new piece of equipment, the 2-degree field, or 2DF capability. And who better to tell us about that than the Observatory Director, Dr. Russell Cannon. Welcome back to the Sky at Night, Russell.
Thank you.
First of all, a bit about the AAT itself.
Yes, well, as you say, it's a very effective telescope because it's fully automatic in the sense that it was designed right from the start to be controlled by computers. It was one of the world's first telescopes to have computer control, and so that means that the pointing and the tracking of the telescope is all done automatically and very precisely, and also all the equipment is controlled by computer, the data taking and so on. And that means that it's much more powerful than the kinds of telescopes that we had before, where you had to sit at the bottom and direct it by hand and take photographs and so on. And the other important technological advances, I think, have come in developments in the light detectors themselves, where the power of the detectors has become much greater. The telescope was designed essentially to do photography. That was the best way of doing astronomy more than 20 years ago. But all these electronic detectors have come in since, particularly charged coupled devices, or CCDs, and they're a factor of 20 or 30 more efficient. And then on top of that, we've done some clever tricks, if you like, with the instrumentation. For example, using optical fibres, so that instead of studying just one star at a time, we can study lots of stars at once by putting the light down optical fibres.
Since the telescope can already do so much, what's the actual need for this new facility?
Well, basically, there's two drivers, I think. I mean, the science is obviously the main one, in that we're always trying to do new, exciting scientific projects, and you've got to keep moving, and as soon as you do one bit of science, you want to see more stars or galaxies, or you want to go fainter so that you're seeing more distant things. And so we're driven to try to always become more effective, more powerful. And secondly, as you know, there are now a new generation of very large optical telescopes being built. The first, the Keck telescope, the 10-metre, is already working. And there are other 8 metres, like the Gemini telescopes that Britain is involved in. And these telescopes will, in some senses, beat us. They're bigger, so they collect more light. And so we've got to be a bit smart to try and stay competitive.
Could you tell us a bit about the design of the 2DF?
Yes, well, as you know, Patrick, the Anglo-Australian telescope was designed right from the beginning to have interchangeable top ends. I mean, we can work at prime focus, where David Mayland sits to take the pictures, or we can work at the Cassegrain focus or at the Coude focus. And to do that, the entire top end of the telescope is lifted off and a different one put on, and each one has different optics, different secondary mirrors to feed the light. When it came to this 2-degree field device, we realized the only way to do it, because it's so large, complicated and heavy, was to build a complete new top end to the telescope. And so we now have 4 top ends. And it's actually a great feature of the design of the AT which enabled us to do this. The fact that we could make a new top end, the fact that the dome was big enough, because you'll see that the 2-degree field sticks a long way out. In fact, it's very tall on the top of the telescope. We've had to rebuild the access platform arrangements to get at it, and the clearance at the crane at the top of the dome, which has to lift it on and off the telescope, is only about 2 inches, and instead of 2 feet.
Not a lot.
And so it's not a lot. It's going to be very dodgy lifting it on and off. But the fact that it's up there and it can be lifted on and off as a unit is another great advantage. In fact, we've designed it so that the optics is up there, of course. The fibre positioner is situated permanently on the top, beyond the optics, and then the fibres come out, run down the sides of the support structure, and the spectrographs are also mounted on the top of the telescope. So the whole device is a self-contained unit. We don't have to unplug these 400 fibres and all the electronics, control cables and everything. It's all a unit. So we can lift it off, and it takes only half an hour to change between doing 2-degree field astronomy to some other sort of astronomy. And I think this is going to be a tremendous advantage, just in practical terms, for using the instrument.
As a matter of interest, what does it weigh?
I don't actually know the exact number. I think they're a bit scared to tell me, because it weighs so much that it's gone a bit beyond what the design was supposed to carry. But the nice thing about the AT is that it was built in the good old days, where engineers doubled the answer when they'd worked out the strength. It's a bit like the Forth road bridge, a railway bridge, I think, with a large safety margin. Well, that's what we're hoping. And in fact, when we first put it, when we first put all the mechanical device on the telescope, Everyone knew it would work, but nevertheless there was a sort of sense of relief around the room when it went on the telescope, and the telescope still worked perfectly well.
Well, this 2DF facility is something entirely new. What exactly is it and what's it designed to do?
Well, the name tells you half the story,
Yes.
2-degree field, and what that means is it's got a field of view of 2 degrees across the sky. And that may not sound much, but for a big optical telescope, it's a very large field of view. Most large telescopes see only a small fraction of a degree. And that means we can cover a lot of sky, look at a lot of objects with it. And the second key feature of the 2-degree field is that we're equipping it with a very large number of optical fibres. In fact, we're aiming for 400 fibres. And so this new device will be about 10 times bigger area of the sky and about 10 times more objects at once than we've ever been able to do before.
How do these fibres work?
Well, basically, I can illustrate this with a rather simple,
Yes.
it's really a toy, a very low-tech version.
It's rather intriguing.
Yes, well, it's a sort of torch, and with a bunch of fibres coming out, and when you switch the light on and off, you can see little stars, nicely coloured stars in this case, appearing at the ends of each fibres. And as I move the fibres around, the light keeps coming down the fibres. So it's very easy to feed the light along the fibres. Now, this is going backwards, if you like. This is sending light up fibres. Yeah. What we do at the telescope now is we mount these fibres inside the telescope so that the end of each fibre is in just the right place to collect the light from one star or galaxy. And then all the fibres come out of the back of the telescope and go together, not into a torch, of course, but into a very much higher tech machine, which is the spectrograph that we're using to observe the stars.
So I imagine the next logical step, then, is to increase not only the size of the field, but also the number of fibres you're using.
Well, that's exactly right. I mean, to take advantage of the field, you need to have more fibres, otherwise there's no benefit in having just the bigger field. And in the old prototype systems that we started with, we had only about 50 fibres, and the first system that was developed in Australia, in fact, at the AT by Peter Gray, our engineer at the time, we had a large brass plate with little holes drilled very accurately in the right places, and you pushed the ends of the fibres into these holes, put the whole thing in the telescope, and away you went when you got it all lined up. The next step was to automate that. I mean, having to drill the holes and poke the fibres in was obviously a bit laborious. And so we had a robotic system, a thing called AutoFib, for automatic fibre positioner, which was built, in fact, jointly with the University of Durham people and ourselves. And that ran around putting the fibres using a little tiny magnet on each end of each fibre to put it on a metal plate. Now, the new system, the 2-degree field, has a very fancy robot which will work very fast and very accurately to put the 400 fibres where we want them.
It's meant a tremendous amount of work and research, hasn't it?
Well, it has. There's quite a lot of technical advances in it. The main optics, for example, is a large lens system to give us this 2-degree field of view, and that has 4 lenses in it, each of which is actually almost as big as the largest refractor telescope in the world. I mean, it's amazing to think that the 40-inch Yerkes telescope has the lens, and our lenses are nearly as big as that. Now, that was an innovation, and we're delighted that that works very well. We've had that now for about 2 years, so we know the optics are good. The positioner, it turns out, is also innovative because to get the precision we want and the speed, we have to be able to place these fibres to an accuracy of about 10 microns. That's about 1/100th part of a millimetre over a field of view which is about 20 inches in diameter. And we also have to be able to do it quickly, because if you're going to put 400 fibres down and you don't want to spend all night doing it, otherwise you're not doing astronomy, it means that we have to place each fibre in about 3 seconds. So we're using linear motors, for example, instead of a lead screw. The conventional way of having an XY motion for the robot would be lead screws, but it's linear motors. And there are many other technical innovations. So each step, we've had to find out how to do it and make it work. It's taken about 5 years altogether to build this instrument.
Well, you have the instrument. It's working.
Yes.
What, in fact, is the ultimate aim of all this research?
Well, it'll be used for lots of different projects, but I think the real driver, the most important scientific one, is to try to study the large-scale structure of the universe, and that's the distribution of the galaxies in space. We know from the COBE satellite, for example, that there is structure in the very early part of the universe. If we look at the nearby universe, the galaxies relatively close to our own galaxy in space, we see that they're very clustered. There are clusters of galaxies and clusters of clusters. But the real question is, how do you get from the very early universe, soon after the Big Bang, to the kind of structures that we see today? And the first step is to try to actually measure the structure. For years, people have been working with the plates from the UK Schmidt telescope, the Photographic Sky Survey, to map out galaxies all over the sky, and they produce beautiful pictures with 1 million galaxies or 2 million galaxies. And when you look at that, you realize that they're not spread randomly on the sky. There's a lot of structure. But when it's only the 2-dimensional picture, you don't really know what that structure is, because we're seeing things superimposed. If you look in one direction in space and measure the distances to the galaxies from the redshifts, because it's an expanding universe, you can do that, you find that the structure along the line of sight, that the galaxies come in clusters, and then there's a bit of empty space, then another bunch of galaxies, and so on. What we really want to do is to measure the three-dimensional structure on the largest scale. And to do that, we need to measure hundreds of thousands of galaxies. Now, in the old days, we used to measure one galaxy at a time with telescopes like the AT, and obviously you can't do 100,000 galaxies if you do one at a time. But now with the Fibres system, we'll be able to do several thousand galaxies a night, and so suddenly it'll be actually quite feasible to measure 250,000 galaxies in 2 years is the target.
I think it's been rather surprised to find out that the galaxies are not just spread round about in space and random. I mean, there's definite structure in the universe,
no,
and of course you're tracking this down.
That's right, but it's quite interesting trying to define what the structure is, and the mathematicians are going to have a ball, I think, trying to fathom it out. If you knew what sort of structure you're looking for, you can say, is there structure with lumps in space? Or if there's bubbles with no galaxies, and the galaxies are formed on the surfaces of the bubbles, like a soap bubble bath. And we don't know which of those pictures is right. Or it might be neither. It may be the galaxies are on wavy sheets or long, snaky structures in space. We just don't know.
It began, in fact, with the Great Wall, didn't it?
In fact, that's a good example. That's right. I mean, people have been doing this business now for already much more than a decade, but going rather slowly. And they found these amazing large structures very close by. But that's with samples of just a few thousand galaxies, and now we want to know how many great walls are there, how far do they go, that kind of thing.
Obviously, this new facility is going to increase your scope tremendously.
Yes, it increases the power of the telescope by another factor of 10 or 100 over what it was already, and so each of these steps gives us another factor of 10 in power. And I think it'll do two things for astronomy. It's not just getting more galaxies, it lets you do new astronomy. I mean, it's new kinds of astronomy that you can do. And that happens in two ways. One is by getting these very large samples to study the structure of the universe, or stars to study the structure of the Milky Way galaxy, the same idea. But also, because we can observe very large numbers observe many objects at once, it means that you can spend time going very faint. And one of the other projects which we're keen to do is, for example, to get the chemical abundances of very old low-mass stars in globular clusters. Now, to get one good spectrum of such a star, down, say, 19th magnitude, will take more than one night on the Anglo-Australian telescope. Yes. So we could never do this job without doing many at once. But because we can spend a week observing the same set of 400 stars, then add up all the signals, it looks like a good use of the telescope if you do 400 in a week, and so you can have a week of integration, a week of observing time on each star, and that again will be qualitatively new astronomy. It's not just more astronomy, it's different astronomy.
You're getting now information about the structure of the universe. Now, what does this tell you about the evolution of the universe and its early history?
Well, that'll be the next question. This big sample I've been talking about, the 250,000 galaxies, are sort of nearby in galaxy terms. I mean, it's immensely distant in everyday terms, but still these are the galaxies close to us, so we see the structure of our universe here and now. But instead of measuring a lot of galaxies over a very large part of the sky, if we concentrate in a smaller area but go very faint, it means we're going very distant. But then because of the expanding universe and because of the light travel time, when we're going very faint, we're also going back very far in time. And what everyone expects is that we will see a difference, the degree of structure, the clumpiness of the universe, everyone expects will be less in the past. But the question is how much less, how did it come? And then we'll be able to work out how the universe evolved from the Big Bang to the present day.
You've got the results now from COBE, the Cosmic Background Explorer satellite, which have been so spectacular. Well, yes. How did that fit in with your new results?
Well, at the moment it doesn't fit, but there's a gap, in fact, between what COBE's done and what we've been able to do so far going back. And the aim of this experiment, if you like, is to try to bridge that gap, if it is bridgeable, and just see how those structures line up.
Have you any idea, really, how many galaxies are going to come within your range with this new facility?
Well, I guess it's infinite if we wait long enough. In fact, the other astronomers who use the AT for many other kinds of astronomy now are a bit nervous about this, because if this 2-degree field takes all the telescope time, they won't get on. And so we will have to be sharing the telescope out, doing lots of different astronomy with it still. I mean, it really is the sky's the limit, I suppose, is all you can say. We could do millions of galaxies. But I think, actually, it's pointless to keep just banging away at every galaxy. What we must do is design experiments and work out what's the most critical observation to make and do targeted experiments.
Well, this 2DF is a pioneering instrument. It's something entirely new, and of course the AAT is the first telescope to be fitted with it. What's the next step?
Well, It's a bit hard to say there. I think when we go beyond this, it's opening up so many new things that I think it will keep us going anyway for several years. And beyond that, one proposal is that we make an infrared version of it, for example, because we're only just starting to explore the infrared sky now. It's an extension of optical astronomy. It's difficult to do it from most of the existing sites. And one proposal is to put a telescope in Antarctica to do a survey for infrared objects, and these generally will be more distant galaxies again. Having found them with a survey like that, then we could have an infrared version of the 2DF on the AAT to get spectra of whatever turns up to explore the universe that way. So that's one future direction that we might go.
At the moment, of course, the 2DF you have on the AAT is the only one of its kind.
Yes.
Are any more being built, and if so, where will they be set up?
Well, I think there won't be any more, actually, because there are very few telescopes, large telescopes, able to take this 2-degree field of view, and indeed strong enough to carry the weight. I mean, it's a huge piece of equipment stuck right at the top of our telescope, and because the AAT was built 25 years ago, it was built with a fair bit of margin in the engineering tolerances and so on. So, in fact, the challenge of the new telescopes is a bit different. They'll be focusing, I think, more on smaller fields or fewer objects, but be able to get more photons, so able to work much fainter. And I think what we'll be doing is finding the interesting objects with the 2DF, and in these 250,000 galaxies, we'll find many extraordinary new objects that no one will be able to understand, and people will then want to study those in more detail with other equipment.
Just one thing more, Russell. The 2DF is a marvellous thing. Was it actually developed by astronomers at Siding Spring?
Yes, in fact, nearly all of it was. We thought about this hard. It's difficult because we don't have a very big team of people. But it's such a complicated instrument that we felt that we couldn't easily just put out a description, a specification, say, build us one of these, because it's unique, it's experimental, and we needed to be able to build a bit and experiment with it and then build a bit more and so on. And so, in fact, it has been done as what you might say, an in-house project at the observatory.
It's only just come into use.
Yes.
When do you expect the first really spectacular results from it?
Well, it could come very fast, actually, because once it's working, in the first hour, for example, we could get more redshifts in a cluster of galaxies like the Coma cluster than have ever been done before. And so if we're lucky and it all works perfectly straight off, we will get some exciting results immediately. The big surveys, of course, will take longer because the whole point of the survey is you have to do a lot of it before you can see the structure, and that will take a couple of years. But we will be using it for all sorts of short one-off experiments, I'm sure, straight away as soon as it's working.
Well, it's a great project, and it underlines yet again the great contribution that the AAT and the observers there are making to astronomy. Russell, thank you very much.
Thank you.
Don't forget, it's newsletter time. If you'd like the latest issue, send your stamped resist envelope to newsletter number 59, The Sky at Night, BBC TV, London W1270S, or dial up CFAX, page 615. And when I come back next month, I'm going to be joined by Dr. John Mason, and we're going to talk about the Leonid meteors. So until then, good night.
Gentlemen. Were Saxon pirates the Vikings of their day? In this, as in everything, they are so elusive. Here in western Norway is still a land of boats. They've kept the tradition of clinker building and rowing and building fine replicas. During the Second World War, Norwegian villagers left these shores in much smaller boats than this and rowed to Scotland, taking their goods and chattels with them. Here the fjord is the way in, and visitors first show on its waters whether they come in peace or war. In East Anglia's muddy, cluttered estuaries, with their marinas and built-up quaysides, the older world is now well buried. But we can't doubt that Anglo-Saxon people were boat people. And the hunt starts here, at Woodbridge, where 1300 years ago, the Sutton Hoo burial ship was dragged out of